Take a look. We have 10 objectives for this section. That's an indication that it might be pretty important. The section is still about sets, though. It's just that now we're going to use special diagrams called Venn diagrams to help visualize some things about sets. Suppose we were talking about a set that contains all the students at Weatherford College. In math, we'd say that's a universal set because it contains all the elements we're talking about right then. In other words, all the students at WC. And we name that set U for universal. If I represented U in a Venn diagram, it would look like this. When you see a rectangle in a Venn diagram, it represents all the elements of whatever you're talking about at that time. Now let's look at some subsets of set U. The first one's going to be set M, the set of students taking Math 1332 here at Weatherford College. The second will be set F, the set of female students here at Weatherford College. We can show those subsets inside of U, and we'll represent those as circles. Those two subsets can have several different kinds of relationships. Let's take a look at the first one. This Venn diagram says that set M is completely separate from set F. Well, what does that mean? It means that there aren't any female students at Weatherford College taking Math 1332. This is how you'd represent that fact in a Venn diagram. These two sets that don't have any overlap at all are called disjoint sets. If you think about it for a minute, who does that leave out here in the rest of U, the universal set? Well, if this circle represents all female students at Weatherford College, that means this group out here is only made up of male students who aren't taking Math 1332. Because if they were taking Math 1332, they'd be inside this circle. Stop and think about that for just a minute. What if I had this situation? What does this diagram indicate? Here are all the students taking Math 1332. They're located inside the set of female students at Weatherford College. That means this set, M, is a proper subset of F. What makes it proper? Well, there's things out here in F that aren't inside of M. And don't forget, we would show that it's a proper subset by this sort of notation over here. Who would that leave out here in the universal set that's not inside of here? Only male students, none of whom are taking Math 1332. Again, think about it. Make sure you understand the relationships going on. What if I've got this situation where set M equals set F? That means that both sets contain exactly the same elements. You could say that a couple of ways. One way, you could say all female students at Weatherford College take Math 1332. Or you could say anybody taking Math 1332 is a female. The last situation looks like this, and you'll see this frequently. This is saying here are students taking Math 1332. It overlaps with the female students at Weatherford College. That means in here, in this area, the area I've shaded green, the people in that group are students who are female and taking Math 1332. Notice there's an overlap, an intersection of the two sets. We're going to talk about that more in just a minute. All we know right now is in that green area, there's at least one student who is both female and taking Math 1332. Please notice this great question. The size of the circles used in a Venn diagram don't have anything to do with how many elements they contain. Keep that in mind. Let's look at example 1. First part says, what's in the universal set? Set U. This, and all three of those. So we have 5 things in the universal set. Next, we're asked, what's in set A? These 2 things right here. And finally, what's in the set of elements in U that are not in A? It has to be this group here. These are not in set A, but they are in set U. Let's look at this example from the book. Set A, blood donors. Set B, breakfast servers. So set A encompasses all of this group. Set B encompasses all of this group. And this area right here, shaded dark blue, is the overlap, the intersection. So out here in the light blue, we've got people that just donate blood but don't serve breakfast. Over here, we've got people that just serve breakfast but they're not blood donors. And then the overlap is the group that does both. The last group out here, they're the ones that they don't serve breakfast and they don't donate blood. They're just out there still in U, but they don't do either one of the other two things. In a similar fashion, over here in example 2, what is set U? It's got these three elements, and these two. So it's got 3, 4, 5, 6, 7 different elements in it. What's set B? It's got the E and the D, so it's got 2 elements in it. The set of elements in A but not in B, well, it's this light blue area here, A, B, and C. We can't count D in there because if D is inside of B also. How about the set of elements in U that aren't in B? Not in B means this one, and these two. Lastly, the set of elements in both A and B. Well, there's only one here in this overlap, and that's got to be D. We know what a set is. What's the complement of a set? The definition tells us that the complement of a set is just everything that's not in the set. The notation looks like this. It's called A prime, and that stands for everything that's not in set A. Let's look at this drawing right here. We can see set A, that's colored white. A prime, in other words, the complement of A, is all this stuff in blue out here. Everything else in the universal set is not in A. In example 3, they're just showing us the same idea with numbers. They're showing us the actual elements in a set. So set A has 1, 3, 4, 7 in it, and the complement of A has 2, 5, 6, 8, 9. There's all of those elements in the universal set. Out here is the complement of A. We talked earlier about the intersection of sets, and back when we did, I said that's just where they overlap. So if you look at these two sets down here, where do they overlap? Right here. So this would be the intersection of those two sets. Get used to the notation. It looks like an upside down U. So this means the intersection of sets A and B. Look at the definition. It says the intersection of sets A and B is every x such that x is an element of A, and at the same time it's an element in B. Just another way of saying everything that's in both A and B at the same time. Example 4 gives us two sets. One of them has 7, 8, 9, 10, 11. The other has 6, 8, 10, and 12. Where do they intersect? In other words, what's common? The elements 8 and 10 are common to both sets. Again, that's where the intersection is. Look at B. One set has 1, 3, 5, 7, 9. The other has 2, 4, 6, 8. Where do they intersect? Where do they overlap? Look at the Venn diagram. There is no overlap. There are no elements in this set that are in this set. It means if we call this set X and this set Y, then the intersection of X and Y is the null set. There are no elements that are in both of those sets. Part C is kind of weird when you see it the first time. We've got a set with 1, 3, 5, 7, 9 in it. In other words, this set that we're calling X intersected with the null set. What's common to this set and this one? Isn't it just the null set? The answer is yes. That's what they have in common, the null set. Another kind of set we can make is called the union of sets. It's the combination of two or more sets. We're just going to look at two sets, though. Look at the definition. It points out that the union of sets A and B is every x so that x is an element of A or x is an element of B. In other words, anything that's either in A or B. Here is an important point. If there's one or more common elements in the union of two sets, make sure you only count those elements once, not twice. As an example, look at part A here in example 5. Here's one set, here's the other set. I marked what's common here. 8 and 10 are common to both sets. So the union would be the set containing 6, 7, 8, 9, 10, 11, 12. Notice the 8 and the 10 only got in there once each. Looking at B, one set has 1, 3, 5, 7, 9. The other set has 2, 4, 6, 8. There are no common things, so I could write that the union is just 1, 2, 3, 4, 5. Let me put my bracket there. 6, 7, 8, 9. Everything in that union is either in the first set or the second set. And finally, part C, one set has 1, 3, 5, 7, 9. The other set is the null set. That means anything in A, anything in the null. Well, there's nothing in the null. So what's the union? It's just all the things in A. So we could say A union null just equals set A. Contrast that with what we found a minute ago. A intersection null equals null. Notice these are kind of the opposites of each other. And it's so important that you realize what I just said. Make sure that you're seeing this down here. It says, again, A intersection null is null. A union null is A. Make sure you understand why. This great question is a good way to remember the difference between a union and an intersection. What happens when we're doing things like finding the union or the intersection and combining that with finding the complement of some of those things? In other words, this kind of stuff right here. The important thing is something you already know from algebra. Do what's inside the parentheses first, if there are parentheses. Example 6 will give us some practice with that. For this kind of problem, I strongly suggest either make a Venn diagram or a list or something. They're telling us what set U is, what set A is, and what set B is. Here's a Venn diagram. Notice in U, I've got all the elements of A, all the elements of B, and then there's some that aren't in either one of those because U has some elements up here that aren't in either one of those other two sets. Let's look at part A here. It's saying do what's in parentheses first. So A union B has 1, 3, 7, 8, 9, 10. In other words, it has everything that's either in set A or set B, and I only count the 3 and the 7 once. They're in the intersection part. So we've done the first part. So now we take the complement of the union. What's left? The 2, 4, 5, and 6. So we get this. The numbers that aren't in the union of A and B. Now let's look at part B. We want an intersection this time. There's no parentheses, and we want the intersection of the complement of A and the complement of B. Maybe a little color would help to see what's not in A. Everything that's not in A is shaded green. So I am seeing 8, 10, 2, 4, 5, and 6. Remember, the order doesn't matter when you're putting them in roster notation. Those are the things that are not in A. In other words, that are in the complement of A. How about the complement of B? A little color helps us to see that everything that's not in B, in other words in yellow, is 1, 9, 2, 4, 5, and 6. The ones in white are in B. So now I want the intersection of the complement of A and the complement of B. What do those two complements have in common? In other words, we want the intersection. Well, 1's not common, 9's not common, 8's not common, 10's not common. That leaves 2, 4, 5, 6. So I can write the intersection of the complement of A and the complement of B like this. Look through these examples. Notice they're showing different combinations of just regular sets, complements, unions, and intersections. Make sure you see why this column out here has the answers that it does. If you see why each one of those works, then you really understand this. Here's our last topic. Suppose I've got sets A and B that look like this. Notice that the intersection of them has D, F, and H in there. What if I wanted to get the cardinal number of the union of those two sets? Now bear in mind, the union of those sets would have A, B, C, E, D, F, H, M, N, P, and Q. It would have all of those things in there in the union. What would be the cardinal number? Well, just looking at it, you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you'd be right. So remember, in this notation, the little n means number of elements in the set. Could I say this? Could I say the cardinal number of the union of A and B? I could just add up the cardinal number of set A and the cardinal number of set B. Well, to find the cardinal number for A, it's going to be 1, 2, 3, 4, 5, 6, 7. The cardinal number for B will be 1, 2, 3, 4, 5, 6, 7. So does that mean that the cardinal number for the union of those two is 14? Let's go back and see here. I'm showing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, what we did before would say the cardinal number of A union B is 11, not 14. What's going on? The problem is, if I just try and do it this way, I'm counting these things twice. Said another way, I'm counting the things in the intersection 2 times. That means I've got to subtract them once. So the formula ends up being the cardinal number of A union B. You take the cardinal number of A plus the cardinal number of B and subtract the cardinal number of the intersection. Let's see if that works. So the cardinal number of A is 7. The cardinal number of B is 7. The cardinal number of this intersection up here is 3. So 7 plus 7 is 14, minus 3 is 11. And that's what we got over here. And that's what we'd get if we just counted each one of these things once. And that's the last thing in section 2.3.